Hi everybody, I'm Rémy. I'm the co-founder and CTO of TuringDB. We are a new fast graph database engine that we built from scratch in C++ because, as I've said many times, we thought that the space of graph database engine basically needs a bit of progress in terms of performance. And right now we are working on ramping up our support of the Cypher query language and to move towards a support of 99% of Cypher, of, let's say, first the common current reasonable subset of Cypher. And so I wanted today basically to just brush up and touch on some basic aspects of Cypher, or maybe not so basic if you are just discovering the Cypher query language, but also what it means when we are designing a graph database engine from scratch, when we are basically implementing query processing, which is how can we execute queries, which are basically just at first streams of characters, right? And how can we turn these characters into something that can act on the database and perform operations and return the results that we want. And if you know already what is a query processing pipeline, basically what some aspects of Cypher implies in terms of that query pipeline and what it needs. Okay, so I will somehow try to make Excalibur work. Okay, so let's start with a simple basic Cypher queries. Let's say I want to match all the nodes A in my graph. And so if I just want to return all the nodes A, all the nodes basically in my graph, I can just write match A, return A, obviously. And so the first thing to note is that Cypher works by basically doing pattern matching over variables. So if I write match A to B with a little arrow like this, and I say return AB, now it matches all the nodes A in my graph such that they have an edge to another node that we will denote as B. And so basically what it returns intuitively is the set of all nodes that are at least connected to something else, that are at least connected to another node. So it won't return, for example, the nodes that are completely isolated in the graph that don't have an outgoing edge to at least some other node. And so basically we can already feel it by the kind of mathematical-like speech that I use by speaking about sets and variables, is that this pattern matching in Cypher here, basically we have to understand it as a universal quantification on variables, which means that implicitly there is a hidden for all A and for all B hidden in here for all nodes A in my graph and for all nodes B in my graph, such that they satisfy this constraint, which is that I have an edge from A to B. So what it returns really is a set of results. So it's a set theoretic description of the results. We could say it's a constraint imposed by the pattern in the match on the set of possible entities that can be returned as a result from my graph. So here it's for all A and for all B such that I have an edge between them and I return them. So that's the description of my result set. My result set is the set of pairs of nodes A and B such that there is an edge between them. And so that's kind of important to understand if we want first to give a rigorous and formal meaning to Cypher in order to actually implement it, in order to actually process cipher queries and implement cipher query processing, right? Our first task as good implementers and good computer scientists would be first to quite understand precisely what we are dealing with. And so to really understand that that set of constraints imposed on the entities present in the database, I could also write something like this. So it means in Cypher, return me all the pairs of nodes A and B, and that's it. Returns me all the pairs of nodes. And mathematically speaking, again, I have my hidden for all quantifier in it, which is basically for all A and B, for all possible A and B, returns me all the pairs A and B. So it's really, really brutal as a query. We must see that it's quite brutal, and obviously, probably in practice we would never do this, but it's quite brutal in the sense that it's really take all the pairs of nodes A and B, meaning like you take all the nodes as a database engine, and you do the Cartesian product to make all the possible pairs between each node, right? Because here I am returning the variables A and B, and I have no constraint whatsoever on A and B this time. Okay, so this is basically the maximal set over pairs of nodes A and B that I can return because I have no constraint on A and B. Okay, so that really illustrates that by default we can return everything, and any pattern matching that we do in Cypher is basically just constraining that set and make it smaller and smaller until we just get what is of interest to us in the job to be done. So I will go back to A to B. If I say now, I'm not interested in all the nodes A, but just some of them with some property attached to them. So let's say if I have a graph of people or actually anything that has an age really in my graph, maybe I just want, if I maybe just return B, maybe I just want all the things that are connected through an outgoing edge to only the nodes with an age of 30 in my graph. Okay, so I may have people, I want all the persons related to the people that are 30 of age, basically. And obviously I could add a label because, you know, in Cypher we are dealing with a labeled property graph, and so I can have labels on nodes, and so I can say match and return me all the things that are related to any person being 30 years old. Okay, so basically, if I return AB, if I return the origin plus the thing attached to A, I basically have, again, a set of pairs, but I have placed now many constraints on those pairs, right? I am imposing that A is a person, that it's not a car, which is 30 years old, that it's not some car museum item, or that is not, for example, a bottle of wine that would be 30 years old, right? So I'm imposing that it is something with a label person, and that indeed the age property is 30, and that I have another entity attached to A, whatever it is. And so this is basically a subset of the overall set of all possible pairs of nodes that we have just seen before, right? It's a subset of the Cartesian product, just with some meaningful constraint. But again, we have to see that everything is, like if we have two variables, this is still a subset of the Cartesian product of all nodes A and B. If we had A, B, C, D, E, F, again, it would be a subset of all the possible tuples. So basically, philosophically, we can understand that query processing in a way is just about evaluating constraints and producing a set of results where we are basically subsetting the data and the result set more and more until we really have what we are interested in. Okay, I could go a bit more like this, and be like, again, for D, I may have a person with age 45, right? And so now I will just return the pairs AD. And so basically what it says is return me all the pairs of persons, of people A and D, such as basically they are related to each other through two other persons, and A has an age of 30 and D has an age of 35. So it's two people. One has to be 30 of age and the other has to be 45. And they have to be related through one hop to B and one hop to C, and from C to D. But like there must be, right, two people called B and C in the middle. So that's the power of variables. Here I don't know the name of B and C, and by the way, I've not even constrained B and C to be actually persons. It depends on what my graph is. It could be anything, potentially. But so I don't know what B and C are. I don't know their name. I don't know if they are persons even. But with variables and with universal quantification, I can say I require that there must be a thing called B and a thing called C after it that relate my two persons A and B somehow. And this is the power of variables, I think. At an intuitive level, if you wish, for the modeling person, it's to say, for all A, B, C, and D, well, find me all the possible connections. Somehow, I don't really care. Or at least I want to know, but I don't know. Give them to me, you know. So for all the possible connections B and C. And so because I don't know what those connections are or should be, I don't have any constraints whatsoever on B and C. So that's basically why we use variables in Cypher, and why variables are powerful for querying, because they are a way to say, to gaze into the unknown somehow, to query the unknown in my graph. Of basically things that may impose connections between potentially entities of interest or even complex phenomena in my graph. So that's about the very simple use of variables in basic Cypher pattern matching. So how does it work in terms of query processing? Well, there is a somewhat simple way of seeing what needs to be done when we are executing that query. It's basically to use what we call streaming query processing, and to see that chain of constraints and that chain of entities from A to B to C to D as a chain of operations and successive filtering that needs to be done using my graph data. So first, we can basically use the good old left to right order and very simply say, okay, we start with A. So one very simple, not optimized, and maybe slightly idiotic way is to start from all the nodes in my database to do what we call scan nodes, which is basically creating a stream, if you wish, of all the nodes in my graph. Obviously, at TuringDB, we are a streaming query engine, and we are working by chunks that are columns. See my previous video if you want to know more about what are columns and what does it mean. But basically, we will stream blocks of data. We will stream blocks of nodes. And the first non-optimized, let's say, pedestrian way is to scan the database for basically streaming the entire set of nodes and streaming blocks of nodes at a time. So I can just start with a scan nodes operator, which is completely unconstrained for now, and just streams me basically blocks of all the nodes contained in my graph. And now I can plug this scan node operation to a filter nodes operation. And so that filter nodes can have a number of constraints, right? I have a label constraint, which is that I am only interested in nodes that are actually persons, that have the label person. And I have a property constraint, which is that the age property must be equal to 30. Okay, so basically what it represents is that we are getting that stream of all the nodes in the database, right? Block by block somehow, with a block size that makes sense. And it's given as input to my filter nodes, and my filter node can filter in some way all the nodes that came in for the label person and for having an age property being equal to 30. And so my filter node will output only blocks of nodes that match these two constraints. And so indeed it acts as a filter on the stream of all the possible nodes given to me by the scan nodes operator. And so now basically I can go into B. And so for this I need a get out edges operation. Get out edges. Okay, and so if I can find, yeah. And so what it does is basically expand all the node IDs filtered previously into their outgoing edges to get basically all the possible B's that are targets of edges starting on the nodes being filtered previously. So now I will have actually a get edge target operation, because I'm only interested in B and nothing on the edge itself, if you wish. It's just the target node of every edge from A that I want. And usually what we do is that we add a kind of virtual operation that does nothing, which is basically what we call a var node, which is just to say that this is called B. Okay, the targets of these edges that I extracted with get edge target are named B, so that we have a sense basically of where are the variables. Actually, now I have to place a var node A as well as at the output of my filter. Okay, if I can make this diagramming tool work. Okay, let's make some space. All right. The arrow is a bit weird, but that's okay. Okay. So yeah, so that's it. You can see that the var nodes have, so this is called a query plan, basically. This is somewhat an abstract representation of the most basic, non-optimized, obvious way of possibly executing that queries for humans. And then we will have obviously an optimization process that will come and start on this very basic plan to try to see what can we possibly improve in that plan, right? Because already there we feel that it's a bit idiotic to scan all the nodes, so return all the possible nodes in the graph, and then filter them a posteriori using the label constraint and the property constraint, where perhaps we could use an index, or we could use some other way to already first query the things that are persons and the things that have an edge, instead of starting blindly, if you wish, over all nodes and only filtering afterwards. But anyway, this is what a basic query plan starts to look like, right? We have operations that are successively filtering and then getting the outages of my node, getting the target, and naming each result so that it maps to the variables A, B, C, and D that I have in my query. So you can see that this plan is basically kind of very, very similar to the textual pattern matching I've written in my query, right? It's nearly homomorphic to my query. It's nearly the same as what I've written syntactically. There is no optimization whatsoever for now. Okay, so my graph starts to be a little big. That's okay. I can just unzoom and make more space. Okay, so I am at B. Now I have to get to C. So for this, we'll add a new getOutages operation, like this, followed by a getEdgeTarget, because again, I'm not interested in the edge here, and I just want to have the target C. So I will name the target as C and put the rows where I need them. So really, in a streaming query processing engine, you really have to see that you have a flow of data which is successively transformed and filters until you get what you want. So now I am at C, I have expanded edges again, and I have to do it again to get to the final end person, D. So I will use the end tool to unzoom and make some space. So what we will do here, so just a look, the person, I'm only interested in nodes that have the label person and have the age property being equal to 45. Okay, what I can do is to expand the outages of C. Very simply, first just gently following the syntax of my pattern from left to right. Okay. And so now I have to filter again. Okay, so I will copy paste my filter node and put another one here. And that will give me really the nodes D that I really want. Okay, so the filter node is placed after the getEdgeTarget node, because indeed I want to filter the targets in order to get D. So I'm only interested again in nodes D that are persons, and now with a property constraint for the edge, for the age being equal to 45. And that is my final variable D. What the fuck? Okay, 1, 2. All right. So just to recap, we were at C, we did getOutages, We took only the targets of those edges, and we filtered those target nodes if they have a label constraint and if they have the age property being equal to 35, and that gives me my node D. So if I unzoom again and we go back to textual query, I can probably enlarge it so that it's more visible. Yeah. Okay. And so you can see roughly that this is somewhat an exact simple translation of my query from A to D, so from left to right, first getting all the nodes, first applying the constraints that we have for A, that gives me A, expanding the edges of A to B, and then the out edges of B to C, and the out edges of C onto D with the filters that we need at the end. Okay, so this is the first query plan generations that we do from the abstract syntax tree of the query, from the syntax of the query. So really a simple, gentle, syntax-directed translation, as we say, which is just about formulating a first plan graph that we can, of course, optimize. It's just to basically go from the world of syntax, if you wish, to the words of query plan, and to start somewhere with some simple query plans that we also know to be correct, or at least we have more confidence that the translation is correct, instead of perhaps having a very convoluted first translation process that would try to somewhat come up with a first set of optimizations. Here we also, for debugging purposes, we kind of like to come up first with a very simple query plan and then do successive transformations of that query plan until we can't rewrite it anymore and we are happy with its final optimized form. And I think this is kind of a wisdom in software development, right? Which is to try to work by successive forms if we can afford the cost, obviously. But it's kind of a wisdom to not try to do too much at once, you know. Okay, so yeah, so this is a query plan. Once this thing is optimized, it will be translated to basically what we call a pipeline of operators, which are really C++ objects that can actually do the operations. So it's also like what people call in traditional database literature as a translation from the logical query plan to a physical query plan, which is really the functions in C++, in our case, that will really concretely perform the actual operations. And we are still at the level of a somewhat abstract representation, because we can see that I have these var nodes that are just basically little decorations just to mark the points where I have the values of each variable in my query. And also the filtered nodes here, you can see that they have a lot of things inside. They have to get the constraints, they have to get the labels of the nodes, and then perform equality on the actual labels of the node and the expected label, and gets the age property. So first, maybe all the nodes don't have an age property, right? And then perform numerical equality on the age property in order for it to be 30, and keep only the nodes that do satisfy this constraint. So we kind of feel at a high level that this is a high level description. This is only a logical query plan, and that physically in the concreteness of execution, if you wish, something more detailed needs to happen. So can I zoom out? Yes. So just to maybe give a little gist of what query optimization could be. Now that we have this query plan, a very simple way to do optimization is to do optimization by successively rewriting the query plan, especially by looking at adjacent operations in this query plan and seeing if they can be combined into a more optimized operation, right? So here it's pretty obvious, for example, that we have a scan nodes and then a filter. Somehow it seems a bit of a waste to get all the nodes in memory as a stream of data, potentially a very big stream of data, very big stream of nodes, to just filter them later and possibly discard a lot of them and just basically generating a huge stream of nodes and being a complete waste potentially, you know, writing a lot of data when it's maybe not really necessary. So here we would like to start from an operation that would maybe generate more what we need right away, or at least be more constrained than just doing a blind global scan nodes operation. So what we can do is take those two operations, scan nodes and filter node, and start to replace them maybe by a scan nodes by label person. So what it will do at least is to just give me the nodes that do have the label person somehow. Let's say I have an index in my database where it's indexed by label set, by set of labels, and I can immediately get only the stream of nodes that have the given label I'm interested in, so that I don't waste time. I don't, as a query engine, I don't spend time just going through all the nodes that may be bottles of wines, that may be houses, that may be countries, whatever. I don't care, right? So just for the sake of making the economy of that time. So I can just rewrite my query plan like this, putting in a row. So now I'm still keeping that filter node, but I can now remove the label constraint because it's basically done by my scan nodes by label operation now, right? Alrighty. So basically now I am just evaluating the property constraints for the age on things, on nodes that are already persons. So that's a bit better. Okay, and then I will not go forward in the details of query optimization, but basically we kind of have a choice here as an optimizer to make. Here I chose manually to first get all the nodes with a label person, right? And then filter by the age equal to 30. That's a choice. Maybe that's a very bad one. I just made it for the sake of explanation and just to give you a feeling of what it means to rewrite a query, right? And to rewrite and combine adjacent operations. But maybe I have a lot of people in my graph. Maybe this is a graph of everybody on Earth and I have billions and billions of humans, right? So maybe scanning all the persons just to subset them later in my filter node, just to filter and keep only the persons with an age of 30, maybe it's kind of a waste because I have way more persons in my population than people with just an age exactly equal to 30, right? So I will spend streaming maybe billions of people just to keep the ones that have an age exactly equal to 30. Or maybe I have the graph of LinkedIn, and there is only some subsets that have an age currently being equal to 30. And so this is kind of a waste, right? So we feel that I could have done another choice, which is first to start by the property constraint. First to start by what are all the things, the nodes that have an age being equal to 30. Maybe the property age being exactly equal to 30. So it's an exact equality. It's not lower than, greater than, and it's a strong numerical equality, let's say intuitively. So we feel, reasonably, I think, that maybe this property constraint is in fact way more restrictive than the label, way more restrictive in the sense that the set of people with an age of 30 in my graph, I mean the set of things with an age of 30 in my graph, may be actually a smaller subset than the set of all people. I think intuitively it makes sense for a human. And so I could have done that. And so you see, as a query optimizer, if I were to be a machine computer program, I don't know. I don't have access to that intuition, right? I don't know. So in general, a query optimizer has many possible choice of optimization to be potentially done, have many rewriting possibilities to be done. And so this is why query optimization is a complex subject in database research, first traditionally in good old relational databases. And somehow an optimizer, we feel that it must have a sense of at least being guided by the characteristics and the statistics of the data, of the graph in our case, and that I could make a more informed choice if I had basically statistics on what's the cardinality, what's the size of the set of all the nodes having a label person versus what's the size of the set of nodes with a property constraint with an age equal to 30. So that we could have an idea of where we stand. Is it more advantageous to first get all the nodes with a label person, or is it more advantageous to perhaps start with the property constraint and just get all the people with an age of 30? Maybe there is, it's likely in this example that there is way fewer people with an age currently being exactly equal to 30, right? So statistics and having a sense of the size of each set to compare is really useful for query optimizers. And that's a thing that researchers in database research figured out a very long time ago now. I mean, depends on what you call the 70s, right? But essentially we can recall the paper of Selinger. I can drop a link in the comments if it's of interest, but if you are interested by database implementation, database engine implementation, I strongly recommend that you take a look at the Selinger paper from 76, if my memory is right, which is about query optimization and saying that actually we should estimate the cardinalities of the sets of data that are likely to be returned by each operation. Here for the label, here for the property constraint, in order to choose, right? Now to make an informed choice. So, and basically Selinger says that we should always start by rewriting to put the operations that have the highest selectivity, which basically constrains the data, the set of data to be returned most, that constrains most the data. That basically enables us to produce the smallest set. So it's all in good sense. It's a very useful heuristic, fairly easy to implement. All right, so that was about what we do with the pipeline. what we do with the query plan, sorry, and now we have to translate it into a query pipeline. I'm going to unzoom. All right, so as I said, this is an abstract representation, and the next step in my query engine operation is basically to translate this abstract query plan, into the things that will actually perform the query, right? Into a chain of C++ functions or C++ classes that will actually perform these operations once this plan has been carefully optimized. And I feel this is an entire subject in itself, and I will probably deep dive into these guys into some other video. In the meantime, stay tuned and please take a look at the docs of TuringDB at docs.turingdb.ai if you are interested, if you think that what I say in this video kind of makes sense. And yeah, don't hesitate to drop a comment and I will answer the best way I can. Thank you very much.